Myself Dinesh. So today I am going to explain about the design and simulation of the circular microstrip patch antenna. So if you are going to design any patch antenna, the basic parameters which we were required to know is the substrate. The dielectric constant of the substrate, that is epsilon naught, the resonance frequency of operation, the height of the substrate. So here in this design, I am going to design an antenna to operate it for 2.45 GHz. And the substrate I have taken is FR4 substrate whose dielectric constant is 4.4 and its substrate height or else the thickness of the substrate is 3.6 mm. So now this is the pictorial representation of this circular patch antenna. So this is the substrate that is having epsilon r. The bottom you have a copper coating that will act as a ground. The top you have a copper coating. In that I am going to design the circular patch antenna. Okay. So this is the general equation to calculate the radius of the patch. That is A is the radius of the patch. So this F that we are calculating this from the mode of operation. So here the F value is 8.791 10 power 9 divided by resonant frequency into square root of epsilon. So this is a standard equation. You just substitute the value of this epsilon FR and epsilon R, then you can directly calculate this radius of the patch. So now we can directly go to the design and simulation of this circular patch antenna in Ancestral HFSS. Now this is the window for the Ancestral HFSS electromagnetic desktop. So here now I have to add the new project. So I added a new project. So in that one, whether I am going to design by using HFSS or Q3D or circuit and Maxwell. So here I am going to design with the HFSS. So I will be clicking this HFSS here. So the HFSS tool is added here. Now in this window you have several sub windows. One is the project manager, next one is the property window, next one is the message manager, then progress window. This is the where the model is being created. Okay. So in this case you have the X, Y and Z axis are present here. So with this axis I have to draw the ground plane, substrate and the patch. So when you take any substrate, so I am taking the XY plane where I am keeping the each and every material in a layer structure. So I will keep a ground plane, above that I will keep a substrate, above that I will keep the patch antenna. So now I will move into the design. So first we will draw the ground plane. So when you come into the top portion, you have the 3D structures here and the 2D structures here. So I am taking, first I want to draw a rectangular. So I am taking a rectangle, clicking at the center, just drawing one 2D structure. So this one I am considering it as a ground. I am going to name it as the ground. Then this is for the transparency, how it looks. If you want to change the color, you can change it. Okay. Now we have to give a dimension for this ground. So I have taken an approximate dimension of 70 and 70. So there is no Z axis because what? It is a 2D structure, XY plane. Just placing it here. Okay. So if you want to fit it into the window, you have a fit all here. Just click it, it will fit it into the window. Okay. So this is how it looks. Okay. Now above this I have to draw the substrate. Substrate is a 3-dimensional structure. Once again I am taking a box from here. Just selecting at the center, then with the same excuse me, I will draw it once again. I'm taking the box, clicking it here, then that's it. So the ground and the length and width of the substrate, both the things are same. So I am drawing a box, I am naming it as the substrate. Then substrate is a material, so I have to choose the material here. This is a FR4 material, just type it as FR4. Okay. Then transparency, I should give some transparency in order to view the remaining sheets. I think it's not coming. Okay. So now you have the ground at the bottom and you have the substrate at the top. Now I have to give the dimension for the substrate. So as I have said in the presentation, the substrate I have chosen is the FR4, that is 4.4, and the height of the substrate is 3.6. Okay. Now I have to give the height of the substrate, that is Z, it is 3.6. Okay, that's all. So if you want to measure it, you just right click, measure, edge. So when I am clicking this portion, so it's showing it as 3.6. Okay, I am just selecting this portion. The height from bottom to top, it is 3.6. Okay. Now we want to design the patch that is above this one. So the patch is a circular one. So I have to draw a circle. Just draw a circle from here. Draw a circle. I am going to name it as the patch. And once again I will give a transparency for this. Okay. Now we have to give the radius of the patch and the patch where I have to place the patch. So usually we will take the center one for drawing the patch. Here I have taken the approximate the center position, that is 37, 35.5, 3.6, and the radius which I have calculated is an approximate value. Finally I have defined it as 17 mm is the value which are giving a good result. So you can able to see you are getting it here. Okay, so this is the value you are getting. So now I have drawn a patch here. This is the patch, and the bottom is the ground plane and the center one is the substrate. Okay, now when you take this any patch, select the object, so if I am taking any patch, at the center you will have a minimum impedance, okay, that will be a zero impedance, and at the end you will have the maximum impedance. So you might have studied in transmission lines, that is we are considering the signal input port, that is a coaxial cable connector or a signal input port, that will be having an impedance of 50 ohms. Okay, so at this end will not be 50 ohm, it will be around 100 to 200 ohms. So when I am directly connecting a line input at this point, definitely the reflection will be takes place here. Okay, standing waves will be generated and reflection will be takes place. So what I have to do, I have to cut a small portion in such a way that the input line, that is a transmission line, is inserting into this circle in order to match with a 50 ohm point. So this is an optimization that we have to do. So we have done the optimization. I will give the final result. So what I have to do, I have to cut a small portion here in order to place the inset fit. Okay, so this one is a 2D section and the strip plane will be a rectangular. So I am just drawing a rectangle in this portion. So this is what I have to subtract now. So I am naming it as subtract, and I should give some dimension for this. Is 40.2, 33, 3.6. Then in x-axis it should be coming up to 14, and y-axis it is 5. Apply. So now I have to cut this portion. Okay. So in order to cut this portion, I will select the patch, then I will select the substrate. Then I will select the subtract. Then in the above, you can able to see unite, subtract, intersect. So here what I am doing, I have to subtract. So I am subtracting this. So after subtraction, I will get a blank portion of the patch, and the subtract portion will be removed, etched out. So okay, so this portion is etched out. Now I have to give a feed. Feed means what? From here I will have a transmission line. It is penetrating into this place, and I have to connect the SMA connector in this place. Now I have to draw a transmission line. The transmission line will also be an rectangular one. So this we will name it as the feed line. Okay, feed line. So I should give a dimension for the feed line, 40.12, 34, 3.6, and it should that is a starting point. Then it should come up to the edge of the substrate, that is 29.9. You can see, so it starts from here and ends. Okay, now both the things are at the top portion. Now you have the patch, then you have the feed line. The input is coming here, moving in this direction, and it is being flown over to the circular patch. So I have to unite both the structure. So I am selecting the patch, control, just press the control key, then selecting the feed line. Then you have to unite both the structures. Just unite. Just see, it is united. Okay. Now if I am connecting a connector in this place, the current will be flowing in this direction, and it will be distributed to the circular patch. Okay. Now where I have to give an input. So this, all the directions, all the structures we have designed is in the XY plane. You just see it is in the XY plane. Only the substrate is having a thickness in the Z plane. Now I have to give the input, that is a port, has to be defined in this place. In this place is what? Where X is constant, only there is a variation in Y and Z. So I should choose YZ plane. So when you see in the upper portion, you have the X, Y, YZ and ZX. In this you have to choose YZ portion. Okay. Then just see this face, zoom it to the center. Once again I have to draw a small rectangular box in order to identify it as the port. So these are all there is no calculation for these things. Only I am connecting the ground with the radiator. Just I am going to assign this as a port. Okay, so this is around 70, 34, 3.6 and all those things. If you are drawing it correctly, then no problem. That is this width and this height. Okay, that is what you have to do. And now I have just drawn the patch, then I have drawn the ground. I have not defined whether it is a material to carry over the current. Now I want to define these two things as a material to carry over the current. So this material I am considering it as, I am selecting the ground, right click, then boundary, and this, it is a finite conductivity material. So finite conductivity, use material. So initially it is vacuum. Now I am defining this material as a copper. Okay, that's all. Now this material will act as a copper. Now once again I'm selecting the patch, going to the boundary, finite conductivity, use material. I'm considering it as a copper material. Okay, that's it. So here I have to give the input. Input is nothing but I have to define how the electric field is moving, whether the electric field is moving in the upward direction or else it is moving from top to bottom. Okay, so here in the HFSS solution type, you have several models. That is where I have to go for a model that is a cavity based structure, or else I am going for a layer based structure. Transient, if I am going to design any circuit, we go for the transient. So here we can go for model or terminal. So I am taking the terminal here and I am going for design. So in this rectangular, I have to draw the port. I am just selecting this rectangular, right click, assign excitation, then I am choosing it as lumped port. Okay, so in this lumped port, you can able to see I have several conductors. One is a patch is a conductor, ground is a conductor. But which I should take it as a reference? That is what it is asking. That is reference conductors for terminal. Usually what we will do, you will have the input in the patch and the reference is a ground. So I am choosing the reference as the ground. Okay. So if I am assigning the excitation, you just see I am getting an excitation. Only one port is there. Inside that you can able to see the what I have assigned a port in this case. Okay, and I have assigned two boundaries. One is the bottom ground plane, another one is the top patch. Okay, so now we have drawn the substrate ground plane, then the patch, then we have also defined the feed, and also we have defined the lump. Now I will click the fit tool. Now this is the thing. I will assign the frequency and it will start radiating. Okay, but if it start radiating, the box which is not defined here, it will consider it as infinite structure. So what I'm doing here, I'm going to draw a box. Within this box, it has to calculate what is the amount of radiation it's taking place. Okay, so I'm just drawing a block. That is the rectangular box. I am drawing it here. Okay, so I am naming it as the radiation box. And I am choosing the material inside is an air material. Okay, it's a free space. And this, it should be very transparent. Then only we can able to see the patch and all those things. And we have given all those. Then now we have to give the dimension. Okay, usually the box, the air box should be greater, that is lambda by 4. With respect to the edge, it should be lambda by 4 out of that. Okay, or else we can give an approximate box in that. So I am giving an approximate air box, that is -10, -10, -23. Then x is 90, then y is 90, and it is 50. Fit all. Just see, this is the air box. So the tool will calculate its radiation characteristics within this box. Okay. So now we have defined all the parameters. Now we have to assign the simulation setup. The analysis is here. Select the analysis. Right click. Add solution setup. Give the frequency as 2.45 gigahertz and pass. Pass is maximum number of us. It will take 20 iterations in order to calculate the actual radiation pattern. So I am giving 20 iterations. Okay. So once again select the setup 1, add frequencies. Add frequency sweep is I have to sweep the frequency from one range to another, as such you are doing it in the function generator. So I am starting frequency is 1 GHz and the end frequencies I am giving it as 3 GHz. Okay, and usually if you take fast means you will get a result very fast and it is little bit accurate. Okay, now we have given the frequency and what is the range of frequency it has to sweep. Everything we have given. Now I am swaying the project, so I am saving it as circular patch for 2.45 gigahertz. Okay, now we have done all the simulations. In addition to this software is having a validation section where it will validate whether all the parameters are being given perfectly. Okay, so when you see it here, it is a desktop view, draw, model and simulation. Just select the simulation that you have a tick mark. There is a validate. Just click it here. It will check whether the design settings are perfect, whether the 3D model is perfectly done. Boundaries and excitation, whether it has done perfectly. Boundaries and excitation means if I am not perfectly defining which is the reference and which is the point where the current will flow. If I am doing it wrongly, then you will have a red mark here. Then mesh operation setup. If I am not giving any setup, also you will get a wrong mark. Radiation setup also we have given. Okay. Now it is validated. Now we go for the analysis. Analyze all. After clicking analyze all, now we have given already that 20 pass it will be taking. Okay, so within the 20 pass, it will be making the solution to very minimum value. So that I will show here. Just see, I have given the delta value is 0.02. So in which iteration I am getting a delta value of less than 0.02, at that iteration it will be stopped and it will calculate the results. Okay, I will show it at the end. Now you just see, this is the progress window, what is happening there. It will be displayed in this particular section. Setup 1, fast frequency we are given. It has been resonating at this frequency. Now everything is perfect because there is no error. Normal completion of simulation on server is completed. Now just click it here. Results. I am going for the solution data. This solution data, I am seeing the profile convergence. You just see, I have given 20 pass. So the total block is divided into several small blocks, that is 775 blocks. Okay. Then for the next iteration. At 13th iteration, it is having around 13,726 small tetrahedral boxes. Within each and every blocks, it will be calculating its S parameter value. Just see, now it is coming very minimum, that is I have defined a target of 0.02, but finally at 13th iteration it is getting 0.01. The difference between the adjacent blocks is very minimum. Now we move once again to the results. Right click, terminal data, report, rectangular. So now when you see this one, this is sweep 1 and primary sweep is we are giving only the frequency and x-axis is a frequency and y-axis is we have to give it. Y-axis we have to find the parameters. So what are the parameters we can able to find? That is a category. S parameter, Y parameter, Z parameter, VSWR, then Z naught, characteristic impedance, group delay. Here we are going to see only the S parameter. Okay. What is the port? I am having only one port, so it is S of 1, 1. And what is the function? Function of S parameter, we consider it as decibel. Okay. So if you see the frequency, it will be displaying for all the frequencies. Now I am selecting new report. So I think there is a small changes, so you're not getting any perfect answer here. Now we will check where the mistake has come. Lamp port, it is defined. I think once again we will give the code. Selecting this, right click, excitation, lamp port, and this. Okay. Okay, I think we have left one condition, that is so I have not defined air box. Air box is a radiation box. Okay, so I am clicking the air box, then boundary I have to select this as the radiation boundary, rad1, and OK. So now we will try it, save the project. I am clearing all those things. Then simulation, validate, so everything is perfect, analyzes all. Now the process is going on. If there is any error that is present inside the structure or any port indefined, so you will be that will be displayed in the message manager. I think it's perfectly over. The simulation is completed. Normal simulation. We will go and check with the results. Yeah. Now we're getting a perfect result because I am not defined that box as a radiation box. Okay. So now I perfectly defined the box as a radiation box. Now you can able to see I am getting a perfect return loss. Return loss is nothing but what? At this particular frequency, nothing is being reflected back. Everything is being radiated also. Okay. I'm just selecting this curve, right click, marker, add maximum. It will go to the maximum one. Select marker, to take the minimum. This is a minimum question where the minimum is 2.44. You can see it's 2.44. Okay. So usually we should take the bandwidth of the antenna. So here, as we have studied in the gain plot and all, you will get a plot in this way. So in that from the maximum you will take minus 3 dB. Okay. So here we will take minus 10 dB as a reference. Okay, that is the tolerance we have considered. So this minus 10 dB, when I am drawing a line in this particular place, you should get the two lines. Okay, I will draw it here. Before that, I will do some modifications in these values. X, Y axis, Y scaling. Minimum is, we can give it as 40, 5 spacing, apply. Yeah, now this axis is changed. Now you can able to see this minus 10 dB. So I will add a marker in this place and then another marker. In this place. Now this I can bring it down. Okay, this also I'm bringing it down. Yeah, now we can able to see the marker 2 and marker 3, it is around minus 10 and minus 10 dB. Okay, so it is 2.39 to 2.48. So this is the bandwidth, 2.39 gigahertz to 2.48 gigahertz. If you want to, so you're getting it as 2.39 to 2.48. So I'm getting it as 0.09 gigahertz. Okay, 0.09 gigahertz in the sense it is 90 megahertz bandwidth. You're getting it here. Okay, so at this particular frequency, you're getting it as what? Minus 37. So when the antenna is below minus 10 dB, it's enough. So it is, you're getting it as minus 30. It is very perfect. Okay, it is perfectly radiating in that particular resonant frequency. Now we will see how the radiation pattern looks like. Okay. So in order to see the radiation pattern, I will come to the model. In order to see the radiation pattern, we should give the angular viewpoint. Those are what? The elevation angle and the azimuthal angle. We have studied the theta value will vary from 0 to pi, and the pi value will vary from 0 to 2 pi radians. Okay. So when you see here, that is, you have the radiation. Okay. Just select it, right click, far field setup, infinite sphere. You have the phi variation and the theta variation. Now I will take it from 0 to 180 degree, and this I will take it from minus 180 to 180. This is the step. This is our interest. We are giving it 2 steps. 0 to 180, 2 step, minus 180 to 180, 2 steps. Okay. Now we have defined this. After defining this, then only when you go to the results, right click, you will get this far field report. If not, you are setting the radiation parameters, you will not get this far field report. So in this far field report, we have to take the radiation pattern. Okay, I am going to take the radiation pattern. This is for 2D. If I want to 3D plus see the 3D plot, I will take the 3D polar plot. I am taking the 3D polar plot. So last adaptive is what? The last frequency which we want to find it out is 2.45 GHz. So at 2.45 GHz, it will be resonating. So primary sweep is phi, secondary sweep is theta. So when I am clicking it here, you can able to see all the values. Okay, what are the values it has taken? 2 degree, 0, 2, 4, 6, 8 and all those things will be here. Similarly, if I go for the theta, there's also the same thing. 2 degree variations it will be plotting. Okay, the frequency is 2.45 gigahertz. Now I have to find the gain plot. So gain total, then the value of the gain I'm going to plot in terms of decibel, dB. Just see, this is the plot it will be plotting. New report. You can see the gain plot of the antenna. Okay, this is the point where phi equal to 0, phi equal to 90, then 180, then 270, once again come to 0. So theta varies from 0 then 90, then 180, then once again it comes to the first point. So you can able to see it here. So how perfectly it's been radiating. Okay, so from this you can able to see it is already mentioned here. The gain is 4.4 dB. The maximum gain this point is 4.4 dB. Okay, so once again if we want to see the directivity, once again the same procedure, results, right click, create far field report. We come to the 3D polar plot, then directivity, total, and this one is the decibel. Okay, once again the same thing, 2.45, all those things are similar, only the output parameter I am getting here. New report, you are getting the value. Okay, both the things are similar. Okay, I think it's looking very similar, but you can able to define this. What is the value, maximum value it has given here? The maximum value is 6.6. In the gain, the maximum value is 4.4. So as you've studied already there, gain is equal to K into D. That is, K is the efficiency into the directivity. If the efficiency is varied, the gain of the antenna will also be. Okay, usually the directivity antenna will be larger than the gain. Okay, so since there is a variation in the efficiency, what happens here? The gain of the antenna is decreasing in this case. Okay, so if you want to see the 2D plot, once again, infinite far field setup, 0, then 90, 90. I am going to take in the two planes. One is the direct eradicated plane, another one is the magnetic field plane. I will show it to you. I have set it. Now results, far field. Now we have to see the 2D plot. So I have to choose this radiation pattern. Okay, radiation pattern. So here we are given two infinite square. One is for 3D plot, another one is for the 2D plot. In the 2D plot, I have given it in the infinite sphere 2. So I am selecting that. Once I am going for the gain total, and this in terms of decibel. New report. Okay, just see, I am getting the two plots. I am getting it here. Only it starts from 0 and it's at what? 180 degree. So I am just changing the parameter. The theta starts from 0, ends at 180. So here I will give it as minus 180. Just see, 0, 180, once again coming to another 180 degree. So totally we are getting this everything. Okay, so this is at phi equal to 0 and this is at phi equal to 90 degree. Okay. So now I'm going for the plot fields, then radiation field, plot, selected. I'm selecting the patch, plot fields, radiation, Okay, I think this is sufficient. Okay, thank you. So today we have seen how we are going to calculate the radius of the circular patch antenna and how we have designed the circular patch antenna. Okay. So now after designing, you are getting the return loss of this 2.44 gigahertz, that is at minus 37.44 decibel, and the bandwidth of antenna at minus 10 dB and minus 10 dB, it is around 90 megahertz we are getting it. The antenna is operating for 90 megahertz bandwidth. Okay, and this is the 3D gain plot, directivity plot, and this is the 2D gain, that is at phi equal to 0 and phi equal to 90 dB. Thank you.